Assalamualaikum warahmatullahi taala wabarakatuh. Very good morning and good afternoon. My name is Dr. Nick. In this video, I will just briefly give you some introduction and maybe a little bit guidance to get you started with your second experiment in laboratory of mechanical engineering, and namely the experiment which is known as kinematic analysis of mechanism. So for this experiment, basically we will just use a software called Mechanalzyer. So it's basically just a simulation where you have to perform a kinematic analysis of different types of configuration with 4-bar and slider crank mechanism. So without further ado, let me share the screen. Okay, what you need to do is basically you have to open the Mechanalyzer, and then sorry. So basically, when you unzip Mechanalyzer, you don't have to install it. It's already what you call portable version of the software. So when you open a Mechanalyzer by double clicking on the file, this will be your main window of Mechanalyzer. Okay, where here is your model, and then on the bottom left is where you can choose different types of mechanism. For example, if I change to slider crank and then click OK, then you will have the slider crank model loaded in the environment. So if you want to simulate the motion for this lab, we will just use the forward kinematic analysis. So if you look at the top right area here, you have the 3 boxes. So F kin stands for forward kinematic, and here is forward dynamics, and the last one is inverse dynamics. So for this lab, we will just use forward kinematic. So if you click here and it says analysis is complete, then only then you can click the play button in order to see your mechanism in action. Okay, so this is with regard to the animated movement result. You can also click on the tab here. If you change it to graph, then you can see all the values for all joints and links. For example, here there are displayed, there are 4 joints and 4 links from the model of a slider crank mechanism. Let's say I'm interested in looking at link 3 or this point here, for example. So if I click link 3 and then looking at the endpoint, for example, I'm interested in the position, and then you can, so just by clicking on your value of interest, for example, in this case, I just click on the position of the end effector. In this case, the endpoint of link 3 for the value in the X direction, which is the blue color, and Y direction in green color. So as expected, since a slider crank mechanism is fixed horizontally, therefore there is no displacement. Sorry, it's fixed vertically, so there is no displacement in Y direction. The only displacement is in X direction and in sinusoidal, kind of sinusoidal manner. So if you want to confirm, you can play again the simulation. So as you can see, there is no displacement in Y, only in X direction. So that explains why you get this type of graph. Okay. So this is basic steps in doing the simulation with Mechanalzyer. There are a few numbers of mechanisms which are already predefined, where you can load them. You have gears. You have, for example, a 6-bar mechanism. The Geneva mechanism, in which you can change the design parameters for each of them. For example, you can change the radius to a bigger radius and add the segment. And then also you can define how many times the rotation should be simulated. Then just hit the F key button. Then you can play the then already you can play the animation. Okay, so based on the lab sheet that you have been uh, given to, basically you have to study two types of mechanism, which are 4-bar linkages and a slider crank mechanism. So since I'm not sure how many of you in the groups, I hope you can divide the tasks within the group, and as well as at the end of the day, you have to exchange the information and write a single report. So for the first part, part A, where you have to study 4-bar linkages, and you can Google Grashof law, what is basically all about. And based on Grashof's law, you can produce 4 types of 4-bar linkages motion, as depicted in this figure here. So what you can do is you just have to play around. Where is the Mechanalyzer? It's here. Okay, you just have to play around. If you load again the 4-bar mechanism, click OK. But when you load the 4-bar mechanism, it is immediately obvious that it does not look similar to the one that we have in the lab sheet or in the Google that you find. Don't ask me why, because this is somehow how the programmer of this software Mechanalyzer is doing it. So however, if you look at this figure, it looks so crowded, and it seems like there are many parameters to be set, whereby in theoretically there should be only 4 bar, only 4 parameters. So if you see here, L5 and L6 are actually kind of uh, extra features that they have been setting in this program. So you can set them to 0. For example, if now I'm set them to 0, then you will end up with a normal bar. So also I, I see if I can set 0, okay, and then for example, just set 2 times rotation, hit the F-key button, then voila, then you have the rotation already. Okay. Um, Feel free to design your own 4-bar mechanism based on Graf's law in order to produce these 4 types of motion. Okay. For example, the one that we have right now, okay, is uh, belong to maybe a crank rocker, because if you see the crank is the like the which are the link that are connected to the motor. In this case, the red link rotates 360 degree. So in this case, it is a crank rocker. Okay. So uh, as explained, you are free to play around with all the lengths of the links, and then if you read the lab sheet further, first you have to plot the position of the end effector. I mean, so for the report, you need to produce the tracing of the position of the end effector. So, for example, if we go back to the model, this might be this link here, which means the L3 link, the end position of the L3 link. So then you go back to the graph, and if you go to link tree and click on the endpoint link and expand it further into the linear position. So okay, this is, for example, the X and Y position of the end effector, if I'm not mistaken. Okay, it should be the link tree. Okay, because if you play again, the link 4, if you see the end of link 4 should be stationary. So in order to verify, you can take a look, expand link 4 and point on link position X and Y, and uh, okay. Oh, so it's basically the same point, L3. Uh, so I just plot endpoint of link 4, which strangely the same as a link 3. So I guess they find in the same link. To click link, link 4. So the coupler, the coupler point is then 0. Okay. So this is one challenges that when you do the simulation and you want to analyze uh, is in order to determine which point is what. Okay, so for that you have to be a little bit creative. For example, if I am interested in this point here, the crank point, which is should be the link 2 and a factor of link 2. can also plot the angular position. So as you see here, this is the angular position of the endpoint of link 2, which is the crank point. So it is in, I'm not sure, I think this is set as cycloidal. Okay, so the input joint trajectory, this is uh, how you are driving, how your motor is driving the mechanism. So in this case, somehow I'm not sure why the default setting is set into cycloidal. You can also change to, for example, to a linear motion. So if you click F kinetic, and then you take a look at the angular position. So now you see that the angular position of the crank, which is connected directly to the motor, is changed linearly until 720 degrees, because we set it to rotation. Okay, you can also set into uh, for example, cosine manner. So yeah, so it's looks almost the same as a cycloidal. So I would say, for the sake of easier analysis later, you should set it to linear. If you can set it to linear, it will be much easier for you to analyze. Okay, so since we have identified that this is endpoint of link 2, and the end effector should be then the endpoint of link 3. Okay, again hit the linear, then position. So this is the x and y position of the end effector. However, for the result section, you have to be aware that the default setting in Mechanalzyer, if you see here, the graph is displayed as the value in y-axis versus time in x-axis. So if you read the lab sheet, the first one here is the position of the end effector. So this is basically, you have to plot y versus x. So this is basically what it means, y versus x. And uh, for this one, position, speed, and acceleration of the end effector versus crank angle. So it's basically, you have to plot, for example, x position versus like the crank angle, and then this one is again, for example, x position versus time. This is already what you already given with by default from the software. So for the first two, of course, this is example x position. You have also to plot y position uh, and y x speed and so on. Okay. So in order to plot 1 and 2, I would suggest you to, for example, in this case, you can export data as CSV. So you can save it anywhere you want. Let's save it. You can save it here. Test Mac and save. And then if you go to the folder that where you save the file, should be a CSV file where you are plotting. It's given the time from 0, and if you see here, the frame is just the number of distinctive frames of simulation that you are running. So in this case, it's 100 time of simulation between 100 points or 100 angles that you should get. And for each point, you have the time as well as the X position and the Y position. So in order to plot the tracing of the position of the and a factor, you can just simply plot X versus Y versus X. So in this case, for example, if you can plot them, okay, I'm not sure whether this is the right one or not. Yeah, just have to check. Insert. Let's choose this one, for example, chart type. Select data. Let's remove the time because it's not needed here. Okay, then it's basically when we want to plot Y versus X. So let's add new one, tracing factor. X should be the x-axis, sorry, the x point, and Y should be the Y point. Okay. Okay. So okay, so it's so it was correct, the original. So this is how the uh, but you have to be careful with the what we call the scaling. The scaling, you have to somehow set the scaling to be equal, so that if not, if it is a circle, it will look like an ellipse if your scaling in x and y axis is not the same. So you should set the x and y axis as the same scaling. Okay, I think that somehow the simulation somehow proved that these endpoints are valid. Okay, and then if you want to do for number 2, if you want to plot the position versus crank angle, you have to extract first for example, we know that the crank is defined as the end position of link 2. Okay, this is the crank angle that goes from 0 degree until 722 degree because it's 2 times rotation. So you can again export this to CSV, or we can do better is you have to first choose also this endpoint position. Okay, but if you see here, because it's no longer visible, but the graph is there actually, uh, because the scale is too big now to display the position, because the scaling goes until 800, which is degree, but on the same curve you have the xy position, which is only the maximum value only 0 point something because it's in meters. So but you know that it's there, it's just not resolvable by our bare naked eyes. So you just have to export data as CSV. So let's call this Mech uh, 2 Then, as previously done, you can open them and plot the so it's already given the unit. This is degree, and this is so. For example, if you want to plot uh, x direction versus uh, you can do the same as previously. Set point, select data, remove this one, add, for example, x versus crank angle. So the x-axis should be the crank angle, and the y-axis should be, for example, the x. So this is how the uh, the x position is changing with the crank angle as the crank goes from 0 to 360, and then it will repeat itself again for the next rotation from 360 degree until 720 degree. Okay, so you just need to repeat it for the y-axis as well. Of course, if you see for linear uh, input here, the input joint trajectory, if you set linear, it will look the same if you plot it versus time. But let's say if you change the trajectory to, for example, to cycloidal, okay, and then run this one, and again you take the crank angle position, now it's no longer linear, versus the x and y position of the end effector, and then export to CSV, Mac 3. Open this file. So now we have it. So you can also simply choose, highlight them, insert. Okay. So of course, if you want to compare two graphs, make sure that the I mean the the scale are uniform for both, then only then you can compare. Okay, so maybe if I can copy this in the same graph of another one, if I put it here, so if you add new data here, select data, add new, and this one is a cycloid. Also choose the x-axis is this one that goes from 0 until 720 degree, and then this one for the x position. Okay. Okay. Sorry. So they look the same, but it's just the point will change. I mean, in terms of the displacement, they produce the same displacement, but only the, I mean, how it change, the displacement between points are different. So you will see the difference when you plot in terms of speed, okay, for these two curves. So I'm really interested in doing this. So let us do now the speed, okay, because for linear the speed is just constant, but for cycloidal the speed, it has a certain kind of profile. So let's do this one. If we plot the speed, save as what I guess CSV. So let's name this as cycloidal speed. Save. And let's compare with a linear. If you input the graph in linear, click this one and see, and take again the crank angle versus the speed of the, and a factor. So let's call this as a linear speed. Save. Let's close the other curve first. Okay, no need to save them. So let's open linear speed and cycloidal speed. So let's just copy the position into the of linear into the cycloid version. This is here. Okay, let's copy here. Okay, and then we can plot. So this should be the linear one. Okay, and then you just need to add select data, add new one. This is, should be the cycloid version. The x-axis is the this one, because this is the angle. Let's take from 0 to 720 degree. And for the y-axis, is the speed in x direction. Should be, I think should be this one. Okay. So see, there goes. It will produce same position in for the both linear and cycloid, but however in speed profile it will change, because you are driving the crank and as well as the mechanism with different input profile. Okay, this is just to demo. I don't ask you to do this analysis in the report, but just try to demo to you the kind of analysis that you have to deal with when using this software. This is not a professional software. This is just education software, free version, and it's not perfect. There are many things that can confuse you, but you have to be smarter than the software. Okay. and that is for the 4-bar linkages. And then when you do the slider crank, first I want you to do some theoretical analysis of the equation. There are two types of slider crank mechanism. The first one is inline, when the base, you can see the base is in line with the center of the crank. But when you have a certain offset, for example in this case by 1.25, I'm not sure, meter or whatever, is referred to as offset slider crank. So please first derive the how you will calculate the position of the end effector, and then only then you do the almost similar thing. In fact, it's a similar thing, the kinematic analysis, except what I want to highlight to you is that when you do the slider crank, it can be quite confusing, because the model given in the software is somehow it's not, first it's not general model because it is an inline model, and secondly it's not really match uh, the model that you have here. So you have to find out what is what by playing around with the parameters here. For example, I just find out the L2 here is not equivalent to the L2 that you can set in the software, because if I change L2 here, you see in the description, the model description, it says L2 is the red bar here, but when I change L2 here, it's not the red bar which is changing. So it's not does not really match. So you have to first find out which parameter is what. And for the offset slider crank, it is defined by this parameter E here. So if I make it bigger, the offset will be bigger. Or if you want to have an inline slider crank, you can just set it to 0. Then it will be an inline slider crank mechanism. So this is, for example, an inline slider crank mechanism. So, but again, you have to really play around and do kind of a reverse engineering in order to match your model with your theoretical calculation here. Okay, and once you finish all the with getting all the data and plotting them, I want you to analyze them and discuss what are the differences. Okay, as well as for part B, for the slider crank, you can compare the simulation results with the theoretical result. Just take a point, maybe at the crank angle 45 degrees, and just check whether your end effector position is correspond to the calculation version versus the simulation version. Okay, so I will stop here. I think you have seen enough. The rest is up to you to explore. And I want to highlight again that this is a free version software. This is not a professional software. We have to be thankful that somebody out there from India who has voluntarily have created this kind of software and shared it to public. But of course, when it's not a commercial software, it comes with not so perfect condition, as I explained earlier. Therefore, you as a future engineer, you have to be smarter than the software and try to do some reverse engineering or reverse analysis to understand what's going on and relate with theory. Okay, so I'll stop here. With that, I would say good luck. and looking forward for your report. Bye.